Hi, welcome to another episode of Mr. Avila Physics. Today we're going to be talking about vectors. As we know from previous unit, vectors are quantities that have both magnitude and direction. Okay? And when we're analyzing problems, sometimes it's very useful to draw a diagram to help us understand a certain situation. Okay? And when we're dealing with vectors, this is very useful. When we draw a vector, each vector is represented by an arrow. And the arrow points in the direction of the vector that it represents. So if I want to, say, indicate a velocity to the right, I will draw a vector pointing to the right. If my object was moving south, I will draw a vector moving south. The length of the arrow is proportional to the magnitude of the vector, and its arrow points in the direction. Okay? So quantities like velocity, displacement, acceleration, among others, are examples of vector quantities. So here we see a car going down the road, okay, and the green arrows represents the velocity of the car at each different point in time, okay. Now, as we can see, the arrow points in different directions, okay. So this direction to this direction to this direction to this direction, this direction. So the direction of the velocity is changing, which means the car is accelerating. And down here we see a scale, right? The scale says 1 centimeter per 90 kilometers per hour. So that means that the length of each of these arrows, okay, for every centimeter of length, it represents a velocity of 90 kilometers per hour. So if the arrow had 2 centimeters in length, that would be a velocity of 180 kilometers per hour. If the length of the arrow is 1.5 centimeters, that means a velocity of 135 kilometers per hour, which is why it's very important to have a scale so that we know what quantity or the magnitude of the vectors represented. Okay? Now, sometimes it's very useful to add vectors. Okay? Now, when we add vectors, we need to be careful, right? Because vectors are different sort of quantities because they have magnitude and direction. So they have to be added in a special way, okay? When we add vectors, our answer, our sum, our addition, is known as the resultant vector or the net vector, okay? When we add vectors, we have two different ways of doing that. We have the graphical method and we have the component method. In the graphical method, okay, it requires precise and accurate diagrams, okay? Vectors must be drawn to scale. So in order to do this, we need rulers, scale paper, protractors, so that we can draw very precise and accurate diagrams, okay? Because we won't be doing any mathematical operations, everything would be done graphically. So it's very important to be very accurate, okay? Now, these first three characteristics are kind of difficult because nowadays very few people actually have rulers and protractors on their backpacks, right? But it also has some good things. When we use the graphical method, it's very easy to see where the resultant vector will be. Also, it's very easy to use when vectors are in the same or opposite directions, meaning when all vectors are horizontal, either pointing right or left, or when all vectors are vertical, either pointing up or down. It's very easy to use this method. It's also very easy to use when vectors are perpendicular, so east and north. That would be simple to do. The other method, by components, okay, it does not require any rulers or protractors or anything like that, right? Because what we do is we break each vector down into its horizontal and its vertical components. We're going to go more into detail about this later. Okay. It does require trigonometry, but it does not. We do not need careful drawing or diagrams. We just need to be able to label things correctly. And this is also easy to use. Let's talk about the graphical method for a second. Okay. So when we use the graphical method, the first thing we do is we draw one of the vectors. Let's call it D1. And we have to make sure that this vector is drawn to scale. Then at the end of the first vector, we draw the second vector, making sure that this second vector is also drawn to scale and that its direction is correct. And then to get the result, I draw an arrow from the beginning of the first vector to the end of the second vector. And this vector will represent the resultant vector. So so the length of the resultant vectors will represent its magnitude, and we can use a ruler to find the length of this vector, okay? And then the angle can be measured with a protractor. This method is known as the tail-to-tip method of adding vectors, also known as one of the graphical methods, okay? The order in which we add vectors does not affect the answer. So V1 plus V2 is the same thing as V2 plus V1. Now, how does this graphical method work? For example, if a person walks 8 kilometers to the east one day and 6 kilometers to the east the next day, then I would draw something like this. I would draw a vector of 8 kilometers according to a scale that I mentioned. This will be 8 kilometers. And then from the end of the first vector, right here, I will draw the second vector, which is 6 kilometers. That would be that. And then my resultant vector would be something like, a resultant vector would be an arrow connected from the beginning of the first vector all the way to the end of the second vector. So this blue vector will be my net vector. Okay. Now, since this was 8 and this was 6, the blue vector becomes 14 kilometers. Okay. Now, if on the other hand, a person walks 8 kilometers to the east on the first day, say something like this, and then it walks 6 kilometers west, so from the end of the first vector, I draw my second vector, right? This one would be 8, this one would be 6. Then my resultant vector will be from the beginning of the first vector to the end of the second vector. This right here, this will be the resultant vector, right? And this would be 2 kilometers east, right? So this is an example of how to use the graphical method when both vectors are horizontal or vertical. Now, another example would be something like this. A person walks 10 kilometers east and then 5 kilometers north. So I would do 10 kilometers east, 1, 2, 3, 4, and then from the end of the first vector, I will draw the second vector, right? Half the size because it's half the length. And then my resultant vector would be, okay, would be from the beginning of the first vector to the end of the second vector. This will be my resultant right here, okay? This would be 10 kilometers. This would be 5 kilometers. And this would be my resultant. In this sort of example, we do not need a ruler to find the resultant. We can use Pythagorean theorems, okay? All right, so in the examples that I've drawn in pen, there's no scale, set. I've just been labeling the vectors. That is not a correct use of the graphical method. Okay, a correct use would be something like this, right? You have a scale right here. We have a scale where each line represents 1 kilometer. So I have a vector here drawn 10 lines. I have a vector here drawn 5 lines to the top. And then I can find the resultant vector by measuring this right here. Okay. So here, okay, our two displacement vectors are represented by the vectors d1 and d2, and the resultant vector would be dr. Okay. So when I take my ruler and I measure this resultant vector, I get an answer of 11.2 kilometers. And when I use my protractor, I get an angle of 27 degrees north of east, okay, or positive 27 degrees. All right. So this graphical method also works when you have more than two vectors. So if I have three vectors right here, I will draw the first vector. It doesn't matter which vector is the first vector. And then from the end of the first vector, I'll draw the second vector. From the end of the second vector, I'll draw my third vector. And then my resultant vector will be from the beginning of the first vector connecting to the last vector. Then I would take my ruler and I would measure this, and I will measure this angle with my protractor, and I would say resultant vector is this many degrees south of east. Now, this graphical method also works when you're subtracting vectors, okay? Now, keep in mind that if I want to do v2 minus v1, that is the same thing as adding v2 plus negative v1. The negative of a vector is just the mirror image of that vector. So negative v1 is just v1 but pointing in the opposite direction. If I wanted to do negative v2 would look like this, right? This would be negative v2, just in case I wanted to subtract v2 as well. Okay, so adding and subtracting vectors is very similar. All right, so that's the graphical method. It is useful if you have rulers and protractors and scale paper or quad paper, but and it's very useful when you have vectors in the same direction or perpendicular, but that's about it. Okay. However, the component method works every time, and you do not need rulers or protractors. When we use the component method, the idea is to break a vector into its components. Okay. Now, the components of a vector are usually one that's horizontal and one that is vertical. Okay. Doing this process means breaking a vector down into its components. So for example, okay, if I have this vector v right here, then to get from this point to this point, I can go along this line, or I can take this path right here. I can go horizontally and I can go vertical. This would be the horizontal component, and this would be the vertical component of vector v, okay, or vx and vy for short. Now, how do we find these components? Okay, in order to find these components, we need to use trigonometry, okay, especially three very commonly used trigonometric ratios: sine, cosine, and tangent. Now, these ratios are found by dividing different sides of the triangle. Okay, so if I have this triangle right here, this is my angle, this is the hypotenuse, right? The longest side of a right triangle. The side that is in front of the angle is known as the opposite side, and the side that is along the angle is the adjacent side. And these three ratios are found by dividing these three sides in different ways. So for example, sine is found by dividing opposite divided by hypotenuse. The cosine of this angle is found by dividing the adjacent by the hypotenuse, and the tangent is found by dividing the opposite over an adjacent. So if I have a triangle that is, this is the angle right here, this is 3, this is 4, and this is 5, right? The sine of the angle would be opposite over hypotenuse. The cosine of the angle would be adjacent over hypotenuse, and the tangent of the angle would be opposite over adjacent. Okay? So, simple enough, right? The only thing that we have to remember is that these ratios only work when we have a right triangle. Okay, otherwise it does not work. How are we going to remember all this? Well, there's a mnemonic for this known as SOHCAHTOA. So if you can remember SOHCAHTOA, then you can remember these ratios right here. So sine equals opposite over hypotenuse, ka, cosine adjacent over hypotenuse, toa, tangent equals opposite over adjacent. So SOHCAHTOA would be an easy way to remember these three trigonometric ratios. Now, these ratios are constant no matter what the size of the triangle is, as long as the angle is the same. So if I have this triangle right here and this triangle right here, okay, the ratios for this angle will be the same. So sine, cosine, and tangent of theta, whether it's this or this, the answer will be the same. Okay? All right. Now, how do we find these components? Well, let's say that we have this right here. We have vector v, right? We have a horizontal component vx, and we have a vertical component vy. Based on SOHCAHTOA, the sine of the angle would be vy over v, right? Opposite, this would be the opposite side, this would be the adjacent side, and this would be the hypotenuse, right? So sine, opposite over hypotenuse, cosine, adjacent over hypotenuse, and tangent, opposite over adjacent. And this, well, this is the Pythagorean theorem. So how do I find Vy? Well, if I know this equation right here, I can solve for Vy, right? Vy would be equal to V sine theta. I can solve for Vx. Vx will be equal to V cosine theta, right? Something like this. Now, these formulas work always as long as theta is the angle that the vector makes with the horizontal axis. All right, okay. So how would I use the component method in a more complicated situation? Let's say I want to add these two vectors, v1 and v2. Okay. If I was doing the graphical method, that would be very simple. I would just take this and connect. I would take my ruler and I will measure this, and I will take my protractor and I will measure this angle right here. But I don't always carry rulers and protractors, so I have to use a different method here. So when using the component method, the first thing we do is we break each vector into its components, right? So horizontal components for each vector, vertical components for each vector. Then once we have that, we add the horizontal components for each vector, and we add the vertical components for both vectors, for our resultant vectors. Then we use Pythagorean theorem to find our resultant right here. Okay? Then we use the inverse trigonometric functions to find the angle that the vector makes with the horizontal. Easy enough? Yeah, but let's make sure that we understand. So here, okay, we have a mail carrier that leaves the post office and drives 22 kilometers in a northern direction. So, okay, I'm going to first draw my axis, right? Okay, so I will draw my y-axis and I will draw my x-axis right here. Yeah, then I would okay, then I would draw my first vector, which is 22 kilometers north. Since I'm not using the graphical method, I don't need to worry about scale. I'll just label this 22 kilometers. And then the second vector is 47 kilometers in a direction south of east. So this is east, this is south, south of east is in this direction. So this would be my vector right here. This is 47 and this is 60 degrees. All right, so how I'm gonna add this vector? I'm gonna find the components for the 47 kilometer vector, because the 22 kilometer vector is already completely vertical. Okay, so this is going to have a horizontal component, which is going to be equal to 47 cosine 60, and this is going to be equal to 47 sine 60, right? So I take my calculator and I find these vectors right here. Okay, I'm back with the calculator. Okay, and let's find this out right here. Okay, so 47 cosine 60 will be equal to 23.5. So this vector right here is equal to 23.5, and this vector right here is equal to 40.7, and this is equal to 40.7. So now I can find a resultant horizontal vector, right, which will be in this direction, 23.5, because there's no other horizontal vectors. And my resultant, so this would be our x, and my resultant vertical vector will be the sum of this plus this. So 22 plus negative 40.7. So 22 plus negative 40.7 gives me minus 18.7. So my resultant y vector will be equal to 18.7. Why am I not writing a negative there? Because the arrow already points down, which means that this is already, the negative is already implied. And then my resultant vector will be this right here. This will be my resultant vector. And my resultant vector will be equal to the square root of 23.5 squared plus 18.7 squared. So my resultant vector will be equal to 18.7 squared plus 23.5 squared, and then square root of that, 30. So the magnitude of my resultant vector will be 30 degrees. To find the angle, I would use inverse tangent of ry over rx. So this is equal to inverse tangent of 18.7 divided by 23.5, and this is equal to the inverse function gives you the angle that has such a tangent, right? So in this case, the angle would be 38.5 degrees south of east. And this will be the magnitude. Yeah? Cool. Let's try another example here and see this one. So pause the video here, take a couple of minutes and see if you can come up with the answer yourself. All right, welcome back. So an airplane involves three parts. Okay, the first is due east for 620 kilometers, so I have to draw my axis here. Okay, so the first one is due east, this direction, for 620 kilometers. The second is southeast. The first one is due east for 620 kilometers, not west. So the first one is due east for 620 kilometers. The second one is southeast for 440 kilometers. This angle is 45 degrees. And the third is at 53 south of west. The third leg is in this direction, where this angle is 53, and this is 550 kilometers. So, what is the displacement? So here I'm going to do, okay, a little table here, x, y, and apparently I'm leaning, okay. So let me try that again. So x, y, y, x, y, then this is going to be 1, 2, 3 resultant. I'm going to find the components of each vector and my resultant. So my first vector is all in x, 0 in y. My second vector, right, here we're going to have 440 sine theta for y and 440 cosine theta for x, where theta is 45 degrees, right, 45, 45. So sine of 45 times 440 gives me 311.13. So the x component is going to be 311.13. The y component is negative 311.13. Why negative? Because it points down, right? So here we have the x component and the y component. The y component points downwards, so it is negative. And for this next one, we're going to have an x component that points this, so it's going to be left, it's going to be negative, and it's going to be equal to 550 cosine of 53. And we're going to have a vertical component that is 550 sine of 53. Okay, so vertical component cosine of 53 times 550 will be negative 331, and sine 53 times 550 is equal to 439.25. So now I add 620 plus 311.13 minus 331 gives me 600.13. So this resultant vector here, this is 600.13. And on the y, I have 311.25 plus 439.25. That gives me minus 750.5. So my resultant vectors will look like this and like this. This is 600.13. This is 750.5. And the plane's total displacement will be from this point to this point with this angle. So the resultant displacement is going to be equal to 750.5 squared plus 600.13 squared, and then square root of that. That will be 960.94 kilometers positive. That's just a scratch. And the direction is going to be equal to the inverse tangent of 750 over 600. Sorry, I'm leaning down. It's hard to write with this pen. Divided by 600.13. Okay. Inverse tangent of that gives me 51 degrees, 51.35 degrees south of west. So the plane total displacement is 960.9 kilometers at negative 51.3 degrees. Oh, okay. Let's try that again. So this would be all right. You get the idea, right? All right. Thank you for watching.